So we were given a whole load of these, and in video 1272 we started taking those apart, and we had lots of really interesting comments, and it was the comments really that prompted this video, because I have here the original foam battery that we've been looking at, an 18650 cylindrical cell, and this beast is from an electric vehicle. And what I want to do is explain the differences between them. The differences are, that one's big, that one's little, and that one's round. That's pretty much it, really. I mean, I'm being a little facetious, so we're going to delve into a little bit more and talk about the differences between these batteries. Now, I do have another one right here, because of course we've got about 1,000 of these things. This one, incidentally, is ruined, and you can tell it's ruined because it's puffed up like a football. What happens when you charge a lithium battery is the electrolyte in there vaporizes a little bit, forms a little bit of gas, and it delaminates everything. If you overcharge it, you get this football shape, and it's completely ruined because it's completely delaminated. If you want to dispose of something like that, you have to actually take it to a disposal centre. And there are disposal centres around. They tend to be in places like computer shops and camera shops, that kind of thing. Now, in here are 4 basic components. So we're going to open this up and have a look at those components. There's a cathode, an anode, an electrolyte, and a separator to keep everything separate. And it's the electrolyte that tends to be the problem, because the electrolyte is actually an organic chemical. It's very flammable, and it has a propensity for doing exactly that. Now, I've been working with batteries for very many years, so I'm about to do something that you really shouldn't do. So it's one of those things, do as I say, not as I do. What I'm going to do is open up this battery and show you the insides of the battery. So phone batteries almost invariably come with a little circuit board right at the top, as we talked about in 1272, whereas these things, they don't. They're just a can with the materials inside the can. This is a bag with the materials inside the bag, and then the manufacturers added a control circuit on top of these batteries. And that's one big difference between a phone battery and a 18650 cylindrical battery. Now, if I rip that off, which I've just done, and we end up with a battery like that, and it's got 2 tabs, it's actually identical to that. There's no real difference between, in fact, there's no difference between these two. So if I open that up, which I can do just by slicing into it, obviously if you're slicing into a battery, you do need to be just that little bit careful not to cut into the material too much, or if it has a charge, it will short. This one is completely ruined. So if I open that up, what we get in there is a roll of material. Okay, that is the battery material right there with the packet removed. If I were to take this out of this metal can, it would look just the same, or instead of being flat, it would be round. And the reason this is flat is because it's been rolled flat. The reason that's round is because it's been rolled round. But the material is identical. It looks just the same. It is basically a layer of aluminium, a layer of plastic, and a layer of copper. So I'm going to open that up and give you a close-up of it. So if we slide a knife down there, we can actually cut open that aluminium and unwind this. There we go. As you can see, it's nothing more than a roll of the materials rolled up flat. When it's in a 18650, this same roll is rolled up in a cylinder. Now if we separate that out, you can see we have a layer of aluminium covered with this material here. There is the separator material there, and then we have a layer of copper covered with this material here. This material is just graphite. So this is graphite mixed with a binder and then pressed onto the copper sheet, and that makes the anode. This material here is the lithium compound mixed with a conductive additive, a binder, and pressed onto the aluminium sheet, and that makes the cathode. So almost invariably in these smaller batteries what you'll find is a roll of material. In these larger batteries they tend to cut them in separate sheets and interleave those separate sheets, but in the smaller ones they're either rolled up flat to make this little flat battery, or they're rolled up in a sausage to make your 18650. Now all of them consist of the same parts, they don't differ at all. So remember, there's an anode which is copper covered in graphite, and all of them have an anode covered in copper and graphite. Then there's a separator, and this separator is almost invariably a polypropylene actually. Sometimes you find that this separator will be a little different in being a tri-layer or a single layer, but they all have this separator material. And then the cathode is always on aluminium. And the only thing that really changes is the makeup of this. And of course every single manufacturer claims the benefits of the particular makeup they use, and we'll go through some of those in a minute. But this section will vary a little bit. Now when you open this up, you'll be able to smell a kind of pear smell, and it's kind of wet. And that's the electrolyte here. When you're looking at something like a lithium polymer battery, then it's claimed the electrolyte is a polymer. Well, it isn't really. Okay, a polymer would be where it would be all solid. What they are is they're gelled electrolytes. They add a polymer into the electrolyte to make it a jelly so that it doesn't leak as much. Those things like polymethyl methacrylate is one that's quite commonly used. But they're a sort of pseudo-solid. They're a gel as opposed to being a solid. These polymers are actually a considerable amount of research when they have self-healing polymers and that kind of thing. But in production batteries, you find this layer of polymer that is wet with an electrolyte. So sometimes the polymer will change a bit, sometimes the electrolyte will change a little bit in its constituents, but it's very much predominantly lithium hexafluorophosphate, pretty much. There's varieties. The electrolyte that you can smell is a mix of ethylene carbonate and propylene carbonate, and again there are various little tweaks that they put onto it, but pretty much that's what they all are. Unless it's a polymer electrolyte, in which case actually it's been gelled with a polymer gel additive. Now this bit here, the cathode, it tends to be what dictates things like cell voltage, and the major parameters of the battery are dictated by this, because this works by donating lithium. The lithium migrates across this separator and is hosted in the graphite. The reverse of that is the lithium goes back to its original side, and that's how a battery works to charge and discharge. Now the ions move across the electrolyte, so the electrolyte has to have the ability to allow ions to move, and the polymer has to have the ability to allow the ions to go through. So this separator just stops these two touching. And it's important that they don't touch, because you can only have ion transmission, which forces the electrons out of the battery around an external path to the other side. And it's that forcing the electrons out of the battery which is where we're able to get work out of it. So we get work out of it by forcing electrons to move external to the battery, and we do that by moving the ions internal to the battery. So if that wasn't there, the electrons and ions could pass and you'd basically get a short battery. So you need that stuff there to keep those two bits apart, so the electrons can't move between them, because of course they would want to, and they can only move outside of the battery in the external circuit that we want to power something with. So that's the role of the separator. That's what the separator does. The electrolyte allows for ion movement. That's the role of the electrolyte. This copper and graphite acts as a host for the other side, and this is the donor. So if you're thinking about something like lithium iron phosphate, for instance, which is what the lithium material in here would be if it was a lithium iron phosphate or a lithium iron cell instead of a lithium ion cell, then that gives it particular qualities for the rate of material and the voltage at which it's at. This is from a Samsung battery, so it's something called an NMC chemistry. Well, that stands for as nickel manganese cobalt, so yes, Samsung batteries contain cobalt. They also have a high voltage version, which is what these are, which is why the charge voltage on this is 4.4 volts. Now there's always a difference between the charge voltage and the nominal voltage. The nominal voltage is the voltage a cell can deliver under specified conditions, that is, under a specified load for a specified amount of time, it will deliver that voltage or at that voltage. Because when you connect a battery to deliver power, you invariably get a voltage drop. That voltage drop is the nominal voltage when it's connected to a specified load. The cell voltage is different to the nominal voltage. That's the voltage at which you charge it. Then when you connect it to something, the nominal voltage is the voltage you would expect. If you connect it to something too big, outside the specified condition, you'll see that voltage drop below the nominal voltage. If it's too low, then you'll see the voltage above the nominal voltage. But when you connect it to the correct loading, you'll see it at the nominal voltage. And that nominal voltage is a specified condition so that you can specify batteries. And when you look on the battery, it will tell you what the nominal voltage is. If you want to know what load that's been tested on, well, you have to look at the specifications, but you can do that by going on the net. Now, the bulk of lithium-ion flavours actually have a nominal voltage of 3.7 volts and a charge voltage of 4.2 volts. However, these Samsungs have a nominal voltage of 3.85 volts and a charge voltage of 4.4 volts. And the reason I know this, it's written on the battery. The other way to do it is to search up the battery manufacturer and get their technical data sheets, and they'll tell you what that charge voltage is and what that nominal voltage is. So there can be a difference in those voltages depending on the material here. So like I say, this is an NMC battery, and so you find it at a slightly higher charge voltage, nominal voltage, whereas lithium iron phosphate actually is at a slightly lower charge voltage and nominal voltage, and lots of other flavours of lithium tend to be around about that 3.7 volts. But you can just look it up, to be honest, and it's often a better thing to do. Now, the reason they have different flavours of lithium is pretty much cost. Lithium iron phosphate batteries are actually really cheap, even though the nominal voltages and charge voltages are lower. They don't last as long, but they are much cheaper. So when you buy a lithium battery, if you're buying a lithium iron phosphate, you won't pay as much, but it won't last as long. If you're buying an NMC, you'll get a higher voltage and a higher nominal voltage, hence it'll have a higher energy density, but it'll be very much more expensive. And so there's a whole range of costs involved with batteries when people make a battery choice on a lithium flavour. Now, lithium is actually kept apart by galleries. It's like a whole load of stacks laid on top of each other. And there are little pillars to keep those stacks apart so the lithium can go in and out. Unfortunately, those little pillars are also made of lithium. So if all of that lithium goes out, then those pillars are gone and the stacks collapse, in which case you can't get any more lithium in and out. Which is why if you discharge a lithium battery down to 0 volts, you ruin it, because you remove all of those pillars, which are lithium, the stacks collapse, and you can't get them back in. There is a voltage at which you can't discharge them any lower, and if you go lower than that voltage, that discharge voltage, then you will ruin the battery, because it will collapse the battery. Now, that's a peculiarity of lithium, to be honest, and it is one of those reasons why you need a way of limiting that with a lithium battery. You can't overcharge them because they're basically full of petrol and there's a little bit of vaporization that goes on, and if you overcharge them, that vaporization gets to a runaway condition, and of course you get fires. So they can't be overcharged for that reason. They can't be left to drain too low or the galleries collapse. So there's a voltage in which lithium batteries can work, and outside of that voltage you either ruin them from over discharge or they'll just burst into flames. And of course we need some way of preventing that from happening, and that's where battery management systems came in. A battery management system, it sounds fantastic, doesn't it? It sounds like it does this wonderful range of jobs. It doesn't actually, it just does that. It prevents a charge going in above a certain charge, and it prevents a charge going out below a certain charge, and it does this by measuring the voltage. Some of the better ones obviously will also measure the temperature of the battery, because when a battery is being charged, it gets hot. If you're overcharging it, it gets very hot. If you read the temperature and you read very hot, then you can turn everything off. And that is what a battery management system does. Now, battery management systems come in a whole range of things, of course, as these things always do. But the simplest battery management system actually is something like that postage stamp little circuit that we've got here. And that thing that we pulled off the top at the beginning of this video is also a battery management system because it does that job. Now that battery management system does a job of making sure that you don't put too much in there or take too much out. And it does that by reading the voltage. Because as you charge it, the voltage will go up. So you charge a lithium battery by applying a constant current. You apply a fixed number of milliamps to it. It'll start at a low voltage, and as the amps go in, that voltage will go up until it reaches its charge voltage. Once it reaches its charge voltage, the battery management system, which is reading the voltage, sends a turn-off signal and no more current can go through. Equally, when you start withdrawing milliamps, the voltage drops. When the voltage drops to a preset level on here, then it turns off the ability to discharge it and no more can be discharged, and that's what that little circuit does. Now, when you're looking at building a whole block of these things and putting these things together, because one of them, I mean, they're pretty useful, eh? I mean, we do all kinds of stuff with this, little garden lights, e-cigarettes, phones, mobiles, all kinds of stuff get done with one. But one of them in itself is not as useful as a whole load that we could put together. And of course, Tesla used a whole load of these to put them into big old blocks so that you could store a ton of power. And here is a block of 18650s put together in a kilowatt hour. Now you'll notice this one is actually in blocks of 12. So they put blocks of 12 and we've got this wire going here and the same on the other side, the negative side, the wire going here. This is the battery management system. It deals with each block of 12 so that the 12 block themselves are not overcharged or over-discharged. But it doesn't deal with each individual battery. It just deals with a block. Again, these are decisions, really. They're cost decisions. So you could, if you wanted, deal with each individual battery by putting a little protection circuit on it, which is exactly what phones do. And each battery could have its own protection circuit. Well, these are only 85 pence each. The battery in here is £5, so it represents a considerable increase in cost if I were to put one on every one. So manufacturers don't. They put them together in blocks and then use a battery management controller, which is just basically a big version of this. It's just doing the same job as this for 7 times, because there are 7 blocks in here. So there are 7 of these, if you like, on that board there, and then an oversight on them. And that's all that board actually does. Now, in these blocks of 12, each battery is left to its own devices. So there may be a bad battery in here, which may well ruin that entire block, but that's actually just a probability thing, okay? These batteries will vary a little bit in their capacity and their voltage and their quality of make. And when you put them together in a block, you're taking a chance that that battery won't ruin the entire block, and it might do. But that's actually just a cost consideration, because we don't want to increase the cost of this tenfold by giving each battery its own, so we club them together and take that risk, and that makes this more affordable. You might think it would be better to put a controller on every little battery, and then you would be perfectly safe with your battery block. And yes, that's true, but that would also make this about twice the price it is. And so in order to sell these things at a reasonable price, because these things are pretty expensive, they make a decision. And when you make that decision, you're making a decision based on the likelihood of that happening. And it's actually quite low, which is why you tend to find these manufactured battery packs in blocks rather than individual ones. So if you're wanting to build a large block of batteries yourself, then again, you have to make that decision. So we are going to put these together in a big block, and we are going to have to make that decision. Are we going to put a block of them together and put one charge controller on them, or are we going to do one each individually with its charge-discharge controller? That actually is what the battery management system is. If I bring those together on a board that registers the temperature, I have myself a battery management system. And that cost I'm willing to pay for that depends on how risky I am prepared to be with a failure of a block, or how protective I want it to be. And that is mostly a cost consideration rather than anything else. So we've looked at the different types of lithium battery, had a chat about how they're made up and why they vary, and they only really vary because of the cathode and sometimes the electrolyte. Then how to deal with them in putting them together in a block, and what a battery management system actually is, which just is a controller for the charge and discharge rate and a temperature sensor. That's it. When we put these things together like this, there is something really interesting to note about these actually. These are little cylinders, and what that means is it's got a gap in there, and of course air can flow through that gap, so that block can be kept relatively cool. If I put a whole load of these together, of course, what I get is a solid pack. That's a big solid pack, and the centre of that can get quite hot. So there's an issue, in inverted commas, with temperature. This one tends to be a bit more self-cooling. This one you need to pay a little bit more attention to on the cooling side of it. Now, of course, NASA have done research on this, and they're doing whole loads of these. It turns out, if you put a little bit of pressure on these, and you put them in a sensible sized block with a little bit of pressure on, they actually have higher capacity and last longer because they don't delaminate as much. So putting a whole pack of these together in a block, like this, will actually give you a battery that lasts longer and has slightly higher capacity if we put a little bit of pressure on it. But of course we do have a possibility of temperature rise in the centre, so that would do really well with a single controller on it, so a single little charge discharge circuit that can handle the amps that's going in there, and a temperature sensor in the middle would make that actually really good. And then we build up those blocks of 10 to make our whole battery, and of course we'd leave areas around that block of 10 for there to be a little airflow, so that we get, if you like, a compromise. Because remember, everything that we do on this is going to be a compromise unless we want our battery pack to cost us £1 million, which we don't want it to do. We want it to be a compromise that is sensible for cost and performance. So something like that actually would make a very good battery pack if you could put a controller on it, because you have to make sure there's a controller on these, even if it's in a block, so you can controlling all 12 or you're controlling just one, because you can't let it go below that charge level, the galleries collapse. You can't let it go above or it will puff out because of vaporization of the electrolyte. So that should, I hope, answer an awful lot of questions that were being asked. What should these things look like? Where does the discharge come from? What are the differences between them, and how would you handle it? Now, basically the differences, remember, are predominantly a difference in cathode material. They get handled pretty much the same way, whether they're a cylinder, a pack like that, an individual one like that, or a block like that. You handle them in the same way. There are slight differences in the flavours of them in terms of their nominal voltage and their charge voltage, but that tends to be really readily available when it comes to looking them up in the manufacturer's datasheet. Anyway, I feel I've rambled on long enough about the differences of lithium-ion batteries and how to use them. I hope it was of interest. Please do remember to like and subscribe, and of course if you have any questions, then by all means pop the questions in the comments and I'll do my best to answer them. Anyway, thank you very much for watching.